The first one is from the Vrije Universiteit Brussels, the University of Brussels, and the speaker is Bram Vanderborght. So let's welcome Bram.
Thank you. So good evening. I want to present how we realize in robotics a twin transition in robotics. Because on the one hand, we need a digital transition, which means saving cost and improving productivity, but we also need a sustainable transition. And we target that in the 3 dimensions: economy, society, and planet. And at robotics, we want to bring the two together in a robotics context. And in order to realize this vision, we need a multidisciplinary approach, because a robot is an integration of the best technologies. That's why we work together with the AI lab, the materials research group, the electronics group, IMEC, and so on. But since we do a lot of human-robot collaboration, also the human, social, and medical sciences are very important, and all of this forms robotics. And we want to create real impact by collaborating with a lot of companies, but during this presentation, I want to present our different startup initiatives. And the first startup we created is called Axillus Bionics. It was one of the papers on 30 years of actuation technologies in our group, mostly on compliant actuators, on locking devices, and so on. And this IP is transferred to the company, and they have now their first medical certified product. We're also having IP on the knee-ankle system, and next month we will present this in Cybathlon in Zurich. So apart from prostheses, we're also developing exoskeletons, and on the market you mainly find passive exoskeletons, which are developed a lot, but the problem is that they often don't support enough and hinder motion in the other motions. Then the number of powered, so with actuators, with motors, exoskeletons are only very limited, but they're often very heavy and bulky. And so similar as with our prosthesis, we want to combine the best of the two worlds, so taking passive elements but also active motors. And so now we're developing our next minimal viable product in order to go to investors, in order to raise money for our startup company, which will be called Husk. In order to do that, we need infrastructure, and that's why we have a €1 million lab called Augmentix, where we have both fixed equipment, like a lot of Vicon cameras, force plates, and so on, but also equipment which is wearable, like IMUs and insoles, so we can measure the ergonomics in situ in a certain factory and then reproduce it in our lab to see what exoskeletons, but also cobots and so on, mean on the impact on the human body. And so this lab is also available for other researchers and companies, and we have a mirror lab, but on rehabilitation robotics on our medical campus. In order to control exoskeletons, we need the intention to move, because only measuring positions is not sufficient. If I want to lift a heavy table, I will not move anyway. So that's why we need to go to the intention to move, and that comes from our brain, but that's very difficult to measure. And that's why we went to develop sensorized cuffs, which have EMG sensors, which are noisy, but an early signal. So we complement that with force pressure sensors, which comes later. And so thanks to the KUKA Innovation Award, we were finalists there, so we got a medical certified cobot, and we made a rehabilitation device. So therapists could very easily program new behaviors, and then when there was an intention to move, we could assist the human. So we also wanted a company on this topic, but the problem was that the robots are very expensive. Moreover, we need to certify again as a medical product, which is a long time to market. And also the reimbursement of physiotherapists, at least in Belgium, is very challenging when using robot technology. So that for this spin-off, which is called Skinetics, we went away from robotics. I hope they will come back at a certain moment. But we go to sports injury detection. So there is a sensorized sport garments, and the idea is that elite athletes will get from the field to their medical team information about the possibility of sports injuries. So a lot of research was on compliant actuators to make it there more energy efficient, but also gearboxes are very important. And yesterday, Osama Khatib mentioned the history, but planetary gearboxes are also very early development, but still today we can innovate and patent on it. And so we listen to ILOS, which is a new spin-off we're also developing.
This is what a truly useful and safe to interact with robot should look like. And this is the pinnacle of what robotics engineers can build today. What's the problem? Today's robots require big and heavy gearboxes and motors to move around. This is known as the hardware problem of modern robotics. How can we make motors smaller? One way is to put more teeth in the gearbox to increase its gear ratio. However, this makes the gearbox clunkier. On the flip side, if we try to shrink the gearbox instead, we just end up with a huge and heavy motor again. At ILOS, we've re-engineered a gearbox with a uniquely efficient planetary movement. Thanks to its novel topology, our gearbox produces higher gear ratios without any need for extra teeth or extra bulk. Our patented technology also minimizes relative movements inside the gearbox, making it more efficient and even lighter. The ILOS gearbox cuts the weight of the motor gearbox duo by 30%, ultimately making the robot up to 50% lighter. The result is an effective and easy-to-control robot that's eco-friendly and truly beneficial. ILOS, shifting robotics into higher gear.
Moreover, we're also looking into new materials. The reason is that robots are very complex, and when they're damaged, we need or costly repairs, or we throw them away. And so that's why we're developing with 20 researchers at the moment self-healing materials. So you see, we cut the material, we bring it back together, and the network polymer reforms. Moreover, we can make it in a portfolio of different mechanical properties, so from very elastic to stiff, but also conductive and magnetic properties. We investigated the different processing techniques, and this is very interesting because we can both mold the system, the material, but also 3D print it. And typically, a networked polymer cannot be printed. You cannot print rubber, for example. And what is very interesting when we do filament printing, then you have the different layers. We have a reaction taking place after depositing the material. So that means the different layers heal together. So we have isotropy in our material, which we think is also a very big potential market for this material. Moreover, we can make the material conductive. That means we can embed sensors in it, for example, for touch detection, but we also use it for measuring pain, measuring damage, but also as a healing network, because we can have both autonomous healing, so after damage it autonomously heals, but if, for example, your gripper is dirty, you want to control when the healing takes place, and that's why we have also non-autonomous healing materials which need heat, and so we can send a current through the conductive material, it heats up, and as such, the actuator can go back to work. And so we developed several demonstrators with it, also multi-material, because how you combine with traditional plastics, for example, different materials, you glue them, you screw them, but then you also have there the weak interfaces. Here we have covalent bonds between the different materials, so the interface is perfect. And there you saw a picture, a video where we damaged the pneumatic finger, and it takes some seconds before we can restore and take the actuator back into action. And this is protected with 7 patent applications, and we're currently developing valence technology in order to go to the market with these materials, which is a vertical platform technology, so we can use it in a lot of vertical markets. And sustainability is on different aspects, because when damaged, we can heal. We can also mechanically recycle it, so we can print the material again, impossible with other network polymers. But we can also chemically recycle it, meaning we can go back to the original monomers and give different mechanical properties to the material. We're investigating or using biosources like castor oils instead of fossil oils, and also investigating biodegradation. So we can make, for example, universal grippers, and here we exaggerated to take a cactus. It will get damaged, we apply heat, the material repairs, and we can go back into action. We also developed self-closing suction cups, very often used in industry. And so typically, if you have a big array of suction cups and want to take a smaller box, then you cannot create enough vacuum to lift it up, like it's happening in the video. But our suction cup, in the design and the materials, hey, it automatically closes, so it consumes much less energy. That also means we can pick up material parts with holes in it, which is often a challenge in industry. And also, we can make it more an octopus-style robot. And again, we use self-healing materials, so also the suction cups can be repaired. As the last spin-off we're preparing, but will take a bit more time. Here in the Sofia project with Arash, we had to lift heavy parts at Volkswagen, so we used the cobot. We had a flexible screen to inform the user, but although the application was very interesting, they couldn't go to the real implementation in the factory. Like 2/3 of the other developments, why cobots are just too slow. And so that's happening a lot at Volkswagen, for example, that they cannot implement it. So what we developed is a perceptor ring with different sensor modalities, so we can make an occupancy map, which is also immune to different environmental conditions, like we filled here the lab full of smoke, and we could still see obstacles and humans. And that means we can move the robot arm fast, and when, for example, a human is being detected, it will slow down and stop, and then rework its path. But that's why we are also interesting, and at the talk yesterday, also very interesting, how we can replan to always have the difference between industrial robots, which are very fast, productive, but slow, and we can when is the difference with cobots, which are slow, but are very safe. And so at Robotics, we have also a booth here, so you can visit us during the coffee breaks and the lunch, where we present these different spin-off initiatives. Thank you a lot.
Thanks very much, Bram. Any questions from the audience? I don't see any questions right now. Well, I certainly found it very interesting with this many spin-offs, right?
Yes, so we can always come to the booth.
Yeah, that's good to point out, actually. They have a booth and they have some very cool hardware there that I would really recommend you to go and see. Let's thank Bram again.
Thank you.